knows a lot about the science stuff. Professor Dave explains.
We are now nearly through the main group elements, with just one group left to go. That is group 18, the noble gases. These are also sometimes called the inert gases, as they tend to be totally unreactive, although as we will see in a moment, that isn't actually true. This group includes helium, neon, argon, krypton, xenon, radon, and oganesson. These nonmetals have electron configurations ending in ns2 and p6, which means they have completely filled valence shells. This is a stabilizing feature, which is why other elements are said to behave so as to attain noble gas electron configuration. What's interesting about the noble gases is that due to their extreme stability, these are the only elements to exist as freely monoatomic species. In other words, a sample of helium is just a bunch of individual helium atoms, unlike all the diatomic gases or metals we've been examining. So where can the noble gases be found? Helium is the second most abundant element in the universe after hydrogen, but interestingly, it is difficult to come by on Earth. This is because of its low mass and lack of reactivity. It is too light to have been deposited in appreciable amounts during Earth's formation, and the little bit that can be found is lighter than air, so it easily escapes out to space. And due to its lack of reactivity, it does not interact with other elements, so as to be found in ores. However, it can be separated from natural gas found in wells, as well as harvested by the capture of alpha particles from the radioactive decay of uranium and thorium, and the United States possesses most of the world's commercial supply of this element. Nevertheless, there is a global helium shortage, and there may come a time where it is exceedingly rare and expensive. Neon is actually the fifth most abundant element in the universe, and it is also lighter than other components of air, so much of it is lost from the atmosphere as well. However, it can be separated from the air by fractional distillation. Argon is a significant component of the atmosphere, making up about 1.3% of it by mass, and this too can be separated from the air by fractional distillation during the production of liquid nitrogen and oxygen. The same can be said for krypton and xenon, though these are less abundant. Radon, like helium, forms from the radioactive decay of uranium and thorium in their respective ores. It therefore percolates from the ground and can accumulate in basements, which can be a health problem due to its radioactivity. And oganesson is our final synthetic transactinide element, first formed in 2006, and its most stable isotope, oganesson-294, has a half-life of less than 1 millisecond, decaying into livermorium-290 by alpha decay. This is the element with the largest atomic number, 118, that can be found on the periodic table. It represents the completion of period 7, which means that if a yet heavier element is ever synthesized, it will require the addition of an 8th period for the first time. In terms of reactivity, there is very little to discuss, since these elements are either inert or too radioactive to last very long. There is one important exception, however, and that is xenon. Xenon is not quite large enough to be significantly radioactive, and yet it is large enough to have a fairly low ionization energy, given that its valence electrons are in the n=5 shell. For this reason, xenon is able to make a variety of covalent compounds, mainly with halogens and oxygen. Xenon can react successively with fluorine gas to form xenon fluorides, and it can also make several types of oxides, such as xenon trioxide, which is an explosive white solid. In fact, even krypton is able to make a select handful of compounds, like krypton difluoride, but it has a greater ionization energy than xenon, so these processes are highly endothermic and therefore limited. Radon has an even lower ionization energy than xenon, so it would be expected to be even more reactive. But again, the radioactive instability makes chemistry more or less impossible, although there is some evidence that radon difluoride does form. So what can we do with noble gases? What purpose could these inert substances serve? Well, helium has one very obvious application that we all become familiar with by our first birthday, and that is balloons. Helium makes balloons float, whether for decoration or for balloons with more scientific or industrial functions. Helium is not flammable, so it is a much better choice for balloons than hydrogen, and this goes even more so for blimps, as anyone familiar with the Hindenburg disaster would agree. Liquid helium is also the best cryogen, since it is the substance with the lowest melting and boiling points in the universe, already existing as a gas at just 4.2 Kelvin, much lower than nitrogen, which boils at 77 Kelvin. Liquid helium is therefore needed for conventional superconductors. Neon also has one application that we should all be familiar with, and that is neon lights and signs. When an electrical arc passes through a low-pressure sample of neon gas, its electrons become excited, and when they relax back to the ground state, they emit photons of red and orange, which decorate busy areas of any major city at night. Argon is used mainly to provide a chemically inert atmosphere. It is the cheapest noble gas due to its abundance in the atmosphere, while also being heavier than the other components, and chemists will therefore often use argon in order to perform atmosphere-sensitive chemistry. This is done by operating under a manifold so that only argon comes into contact with the liquid-air interface rather than other more reactive atmospheric components like oxygen, nitrogen, carbon dioxide, or water. Additionally, argon is used in modern incandescent light bulbs and as a shielding gas in industry. Krypton is also used in incandescent light bulbs as well as electrical discharge tubes. Because krypton is heavier than argon, it allows for the slower evaporation of a tungsten wire, which allows the wire to remain hotter, leading to a larger proportion of electromagnetic radiation emitted in the visible range. Xenon is also used in incandescent bulbs for precisely the same reason, and has more applications still. Xenon flash lamps are used by photographers. Xenon 133 is used for the medical imaging of lungs. Plasma displays utilize xenon and neon excited by electrodes. Xenon is a propellant for ion drive engines, and it is even used as a general anesthetic. Radon has no official applications and is recognized as the second biggest cause of lung cancer. It is likely the cause of so-called radioactive rainouts, where radon-222 that escapes into the air decays into polonium-218, lead-214, and bismuth-214, and the daughter products are collected by drops of rain. This causes the rain to be dangerously radioactive for 30 minutes or so. And as is no surprise, with its ultra-short half-life, oganesson serves no practical purpose other than a demonstration of our prowess with a particle accelerator, and our ability to briefly defy nature by building atoms larger than she seemingly intended. And with that, we wrap up our survey of the main group elements. Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.